So this lesson is on logistic differential equations, which are a type of first-order differential equation. Before we talk about logistic differential equations, let's review a differential equation where the rate of change of something is proportional to the value of that thing. In this case, that thing is y. This is a type of differential equation that we talked about earlier in the unit, whose solution, because it's a separable differential equation, was y equals c e to the k times t. So the solution to this differential equation is an exponential function, either a growth or decay function. And in this case, we're going to assume it's a growth function. And inherent in this assumption is that this function assumes unlimited growth. So it will grow forever, and it won't stop. Most population models end up stopping at some point. Nothing grows exponentially forever in terms of population growth. And so this is where logistic differential equations are going to come into play. So a logistic differential equation is going to look very similar to our first equation here. Except it's slightly different. So it has the following form. dy dt is equal to k times y. So same thing so far. But what we're going to do is we're going to multiply k times y by 1 minus y over L. Okay? And we're going to talk about what that means and what it does to the solution after we go through this derivation. So this is a logistic differential equation, where L is called the carrying capacity. So let's what we're going to do here is let's solve this for y. So we're going to solve this logistic differential equation. To do that, we're going to separate the variables. This doesn't look like it, but it's a separable differential equation. So I'm going to move all the y's to one side, and I'm going to move the dt over to the other side with the k. On the left-hand side, we get 1 over y times 1 minus y over L dy equals k times dt. And so now that we've moved the variables on one side, now we can integrate both sides. The tricky thing about this, I think, is this L here. This L is just a number, and so it's not a variable, so we're going to leave it over with the y's for now. Now let's integrate both sides. The right-hand side integration is not going to be too bad. The left-hand side is a little bit more challenging. So before we integrate this, let's actually rewrite this. This is not something we know how to integrate just yet. We need to rewrite it in a different form that makes it something that we can integrate. And to do that, we're going to do a couple things. The first thing we're going to do is multiply this by L over L. What that will do is it's going to change this by we're going to write an L in the numerator, and then on the denominator we get y times L minus y. And the reason we're going to write it like this is because we can break this apart now by doing a partial fraction decomposition. Like that. Okay. So, remember when we're doing a partial fraction decomposition, we want to solve for a and b. And then that's going to bring this into a form that we can integrate. So to do that, we're going to multiply everything, this whole equation, by y times L minus y. And if we do that, on the left-hand side, we just get L. And then the right-hand side becomes a times L minus y plus b times y. Let's distribute the a to both these terms here. And now we can use this to solve for a. Because there's only one L term on the left-hand side and a is the only thing on the right-hand side that has an L, a has to be 1 in this question. So let's plug that in. L is equal to L, because a is 1, minus y plus b. Now let's use this to solve for b. So if we solve for b here, sorry, there's a y right there. The L's will cancel. And 0 is equal to minus y plus by. We can move the y over. And we get y is equal to b times y, so b is equal to 1 as well. All right, so what that means is we can take the function here and we can rewrite it like this. And so I'm going to rewrite this whole thing down below in a second, but we can rewrite this like that. Okay, so now let's integrate the left-hand side of this equation. So remember, what we're doing here is we're solving for y. So here's our left-hand side. And the right-hand side is still this right here, the integral of k times dt. So the reason why we did the partial fraction decomposition is because now this is in a form that we can easily integrate. So let's integrate both terms here. The integral of 1 over y is the natural log of y, plus, well, it's actually going to be negative because you can do a u substitution here. And what will happen is a negative will get pulled out, and we get minus absolute value of L minus y is equal to k times t plus some constant c. All right, minus y. So we want to solve this for y. So we're going to do a couple things. The first thing we'll do here is let's change the order around and multiply everything by a negative 1. So we get natural log of 1 minus y minus natural log of y equals negative k times t plus c. And we can combine these together by using properties of logarithms. Remember, if we subtract two log statements, we can divide the inside. Is equal to minus k times t plus c. Now to get rid of the natural log, we're going to exponentiate both sides. So the left-hand side is just going to become L minus y over y. And the right-hand side, well, what we can do is, we've done this in class a couple times, this c can essentially come down to the front. I'll write out the steps here. Because e raised to c is just a constant, so the right-hand side becomes c e to the negative k times t. Okay? And let's break the left-hand side apart. So L over y minus 1 equals c e to the negative k times t. And we're going to add 1 on both sides. So we're almost done. So we're going to add 1 on both sides. And then what we're going to do is basically, we could switch these around, multiply by y on both sides, and then divide by c e to the negative kt plus 1. And so what happens now is y becomes equal to L over c e to the negative kt plus 1, where c is defined as, and we can prove this by plugging in 0 for t, L minus y0 over y0. And this is the initial value. When t equals 0. So this right here is the solution to the logistic differential equation. What I would encourage you to do is write this down and recognize quickly that it's the solution, because if you're ever asked to solve a logistic differential equation, you can skip straight to this part right here, and you don't have to worry about going through that whole process of solving this. Okay, so what does this look like graphically? What are the solutions that these look like graphically? Well, we know that when we were dealing with just the normal exponential function, which was our solution, exponential functions look like that. This is going to be different though. So this is y is equal to c e to the k times t. The solutions to these are different because what happens is they level off at a value here. That value is called the carrying capacity, which we talked about a little bit earlier. So this is the carrying capacity right here. And so what the solution of a logistic differential equation will look like is, instead of just trailing off upward forever, it will go up, and then it will level off at this carrying capacity. So this is y is equal to L over C e to the negative kt plus 1. Okay, so the solutions are different. So this is going to be y over here, and this is t. So for a logistic differential equation, an important thing to recognize is as t approaches infinity, the value of the solution will approach the carrying capacity L. So it kind of levels off. The best analogy to kind of think about how this works is think about a population of some animal with finite resources. That population can't grow forever. It will kind of level off once they use the proper amount of resources to kind of sustain their population. Okay. One more thing before we move on to our first example is an important characteristic of this is that not only does it level off at the carrying capacity, but at L over 2, which is half the carrying capacity. So this is L over 2, I'll write it over here. Y increases fastest at L over 2. So the rate of change of the solution increases fastest at half of the carrying capacity. That can be proven by using the second derivative. We don't have to go through that derivation, but you can prove it using the second derivative, or the derivative of the logistic differential equation. Okay, let's go through an example. So our goal here is to solve a logistic differential equation. All right, so some practice. Let's say we have a population of wolves, and they're modeled by the following differential equation. What we're going to do is we're going to find the solution to this. We're going to solve for W, and then use that solution to determine the time it takes the population to reach 350. So notice the value 350 is greater than the carrying capacity 300. So what's the initial population 500 is greater than the carrying capacity 300, and so what's going to happen is the population of 500 will kind of tend to 300, and our goal here is to determine how long it takes for the 500 to reach 350. Okay, so it's a little tricky, but let's go ahead and solve this. So we could go through the entire derivation or we could quickly recognize kind of the key features here. The first feature is that 0.8 is our K value. It's a growth factor or decay factor. The carrying capacity is 300. It's right here. And then the initial value is equal to 500, and that's given to us. The solution to this differential equation, W, is going to be equal to L, carrying capacity, over C, E, to the negative KT plus 1, where C is defined as, we talked about this earlier, where C is equal to, if we go back, it's L minus, well, in this case, it's not Y, but it's W naught, initial value, over W naught. And so the C value in this case is going to be 300 minus carrying capacity minus the initial value, 500, over 500. This is negative 0.4. So we'll plug that in for C. So we have a couple things here. We want to figure out the time. To solve this question, we want to figure out the time t it takes for the initial population, to reach 350. All right, so 350 is going to be our final population here. The carrying capacity is 300. The constant that we just derived is negative 0.4. E to the negative 0.8, that's our K value, T plus 1. And our goal here is to solve this for T. So the trick here, the reason why we went through the derivation is because we can go straight from the logistic differential equation to the solution here. Now that we have an expression that represents the solution of this differential equation, we can use it to solve for T algebraically. All right. So to do this, we can rearrange this a little bit. Let's multiply by the whole denominator on both sides and then divide by 350. So this is the same thing as the following. Okay, so again, we can switch these around. So let's subtract 1 on both sides. Well, this is 6 over 7 minus 1. Okay, so negative 0.4 e to the negative 0.8 times t is equal to 6 over 7 minus 7 over 7. So negative 0.4 e to the negative 0.8 t is equal to negative 1/7. Well, the negatives can go away. And now this is a 4 here. Kind of looks like a 9. Now let's multiply by the reciprocal of 0.4, which is going to be 10 over 4. So e to the negative 0.8 t is equal to 10 over 28. So 10 over 4 on both sides. And now remember, if we want to solve for t here, we're going to take the natural log of both sides. So instead of the natural log of 10 over 28, we can do the natural log of 5 over 14. Same thing. So we get negative 0.8 t is equal to the natural log of 5 over 14. And so the t value here is negative natural log of 5 over 14 over 0.8. And if you plug that in your calculator, it's about 1.287 years. Okay, so basically what's happening here is, in this case, these wolves are greater than the carrying capacity of 300. So this is W and this is T. Imagine the wolves population is like up here at 500. And we're figuring out the time it takes for the population to reach 350. Okay, so regardless if the function is above or below the carrying capacity, it will tend to that value. Okay, so as t approaches infinity, the population of wolves will approach 300. All right, let's wrap up this video by doing one more problem set. The first part is a logistic differential equation, and then the question kind of changes. So these are two questions that are a little bit more conceptual. So here we have a logistic differential equation that models population growth. For letter A, we want to determine the value of the limit as t approaches infinity of the solution of this logistic differential equation. So there's two ways you can think about it. The first is kind of mathematically, we know the solution to this. We know the solution to this, P, because we went through the derivation, is C. C is going to be some constant. It'll be determined by the initial value, but it's just a number. E to the negative 0.2 t plus 1. Okay, so one way you can think about this question is regardless of the initial position, the C value, the limit of this function, the limit as t approaches infinity of P is going to be the same number. And the same number, that number is going to be the number 12 because this will tend to 0 if you plug in infinity. And the reason why it's 12, regardless of the initial position, is because if the function is above or below the carrying capacity, the function P, the solution of the differential equation P, will approach the carrying capacity. And so the solution to this limit is equal to 12 because the carrying capacity is 12. So this is the carrying capacity. So that's the other way to think about it, is it's all this is asking is what's the carrying capacity. All right, letter B. If P of 0 is equal to 3, when is the population growing fastest? Well, we talked about this earlier. The function, the population, grows fastest at half the carrying capacity. So what is half the carrying capacity? That is going to be 12 over 2. So it's 6. So that's the p-value where it's growing the fastest because that's half the carrying capacity. So those are the two logistic differential equation questions here. This question right here, letter C, is a separable differential equation, which we're going to use to solve for y. Okay, and so we're going to wrap up the video by going through this separable differential equation. And I would encourage you, before we go through this, to stop the video and try to do this on your own. So we want to solve this separable differential equation. We are given an initial position of 0, 3. Y of 0 is equal to 3. Okay, so let's solve this separable differential equation. And that will wrap up the video for today. So to solve this separable differential equation, let's bring all the y terms to one side and all the t terms to the other side. So I'm going to divide by y on both sides, and then multiply this 1/5 through to get the following. Now let's integrate both sides. So the natural log of the absolute value of y is equal to t over 5, it's the integral of 1/5 with respect to t, minus t squared over 120 plus c. Let's exponentiate both sides, so e to the ln of y is equal to e to the t over 5 minus t squared over 120 plus c. The right-hand side, or the left-hand side, sorry, becomes y. And we've seen this before, the c can come down here in the front. And now we're going to use this is a good spot to use the initial condition to solve for c. So the y value is 3, and the t value, or the x value, is 0. So 3 is equal to c, which is what we're solving for, e to the 0. So c is equal to 3 here. We're going to take that, plug it in over here. So the solution to this, or the particular solution to this differential equation, is 3e to the t over 5 minus t squared over 120. Okay, so that's the answer. And now the last part of this question wants us to evaluate the limit as t approaches infinity of 3e to the t over 5 minus t squared over 120. Okay. The difference between this question and the last question is this is not a logistic differential equation. And the reason for that is this would have to be a y for it to be a logistic differential equation, which means that the limit as t approaches infinity is not the carrying capacity. So we're just going to evaluate this like a normal limit. So we can rewrite this. T, or 3 times e to the t over 5 over e to the t squared over 120. You can break this apart. All right, now we're going to plug in infinity. This is a little sloppy, but I don't want this video to go too long. Now if we plug in infinity, we end up with a higher degree term in the denominator, so this will tend to 0, and that's our final answer.